This is Chapter 11, Section 2. We're going to look at several gas laws in this chapter, and we're going to cover the first four today. The first of these gas laws is called Boyles Law. You do not need to write down this data here. It's more important that you understand what's going on with the data. So as I look at this, I'm going to look at the data there under volume. As you move down these numbers, the numbers increase, and as you move down the same experiment, as you move down pressure, pressure decreases. So if you have two variables that move in opposite directions, they are said to be inversely proportional. And we've talked about inverse and direct proportions before. But when you multiply the two variables, pressure times volume, you get essentially a constant value. So that's going to be essentially constant. Data that you do need to get down, though, if you were to graph this data, and this was something like what we did, sorry about that, something like what we did back in Chapter 2. If you were to graph this data, you would get a hyperbola. Pressure can get really close to the y-axis without touching. Volume can get close to the x-axis without touching. And when you multiply the two variables together, P times V, you get K. So, for Boyle's Law, you're going to look at pressure and volume being inversely related. Mass and temperature are kept constant. Let's go look at a video of Boyle's Law being demonstrated.
In a demonstration of Boyle's Law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum, which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's Law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's Law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
So again, for Boyle's Law, as pressure increases, volume decreases, or vice versa. If volume increases, pressure will decrease. The second law we're going to look at is Charles's Law. And again, you don't have to write down this data. It's more important you understand the relationship. So if I look from experiment 1 through 4, the volume is increasing and the corresponding temperatures are also increasing. So if you divide the two variables, you get essentially a constant value. So with these, since they move in the same direction, increase together or decrease together, you would get a linear graph whenever you looked at this data. And again, volume divided by temperature is going to be equal to a constant value for a given substance. Hold mass and pressure constant. And temperature for this chapter, anytime we're dealing with gases, temperature will have to be calculated on the Kelvin temperature scale. We will briefly look at the Kelvin temperature scale again momentarily. Let's go look at that now. Kelvin is equal to Celsius plus 273 degrees. We knocked off the 0.15 for that, but again, a lot of times these temperatures are going to be given in Celsius, but to work out any of the gas laws, your temperature must be in Kelvin to work out the gas law problem itself. It must be in Kelvin. Now we're going to look at a demonstration of Charles's Law.
As an illustration of Charles' Law, We will cool a sample of air trapped in a balloon. As we cool the air, the molecules of...
This balloon is basically one of those really long, skinny balloons like they would make balloon animals out of.
...in the air slow down. This decreases the pressure inside the balloon. The volume of the balloon contracts until the pressure inside the balloon and the outside of the balloon are equal. The volume of the gas is directly dependent upon the temperature of the gas. When we remove the balloon from the liquid nitrogen, the temperature of the gas increases. The volume of the gas expands until the pressure inside the balloon and the outside of the balloon are equal again.
Again, for Charles's law, we are looking at volume and temperature. Volume and temperature will increase or decrease in the same direction. Third law is Gay-Lussac's law. Again, this data, if we're looking at it, you have a temperature that is increasing in this direction and the corresponding pressure also increases. When you divide the two variables, you get essentially a constant value. So temperature and pressure of a gas are going to be directly related also. If you were to graph it, you would get a linear graph. Again, the two variables increase or decrease together, and if you divide the two variables, you get a constant value. Depending on your substance, that constant value changes. So in this one, mass and volume are going to be held constant, and again, temperatures still have to be on the Kelvin temperature scale to do any type of gas law calculation. Let's go look at an example of Gay-Lussac's law. So these right here are called hand boilers. This is an enclosed glass system, and it has a liquid inside that's really alcohol. And when you apply heat from your hand, it changes the pressure inside the system. The volume of the liquid cannot change since it is a closed system. Now, if you just let it set, if it gets to room temperature, then the liquid will fall. They're applying heat right here back to the top. Again, changing the temperature at the top, the pressure will change again to move the liquid back down to the bottom. The rest of this video does show how exactly the hand boilers work and where temperature is being changed as far as the air inside. So that was Gay-Lussac's law. Again, we were changing the temperature of the hand boilers by just applying our hands to it because alcohol does boil at a temperature below what our body temperature is, and that in turn changes the pressure inside the system. So as temperature increased, the pressure inside the system also increased. Now, before we get to the combined gas law, I do want to show you all of the gas laws that we've had so far. So we've had Boyles Law, and with the Boyles Law, we were looking at the changes in pressure and volume. So pressure times volume would give us a constant. And with this right here, we did have a graph that was a hyperbola for our graph. Then we had Charles's law. Charles's law looked at volume and temperature, but this time volume divided by temperature would give us a constant, and the graph was considered to be linear. And then that third law we looked at, Gay-Lussac's law, it looks at pressure and temperature, and again, pressure divided by temperature is equal to a constant value, and also gave us a linear graph. So when you divide your variables and get a constant, they are directly related. Remember, divide and direct both start with the letter D. Now we're going to introduce to you the combined gas law. And the combined gas law is going to take into account all of this into the combined gas law. And notice temperature is in the denominator. So with our combined gas law, this is the fourth gas law you're going to learn. We're going to look at combining. We've got Boyle's Law, Charles's Law, and Gay-Lussac's Law to give us PV over T equals a constant. Now, the ones and the twos, You could think of that as beginning, end, start, finish, data points 1, data points 2, initial, final, whatever you want to look at it. But they are putting the 1s and 2s. And I do like to rearrange this stuff so that we don't, if possible, don't have anything in the denominator. So I'm going to bring T1 and T2 out of the denominator, which means I have to multiply T1 here and here. And then T2 also gets multiplied here to cancel, and you'll have T2 on the other side. So when we look at this, this is the equation you're going to see me use over and over for the combined gas law. So make sure you get this as your final equation for combined gas law, and notice your temperatures have been reversed. So you have T2 on the left and T1 on the right. And again, all temperatures must be in Kelvin whenever we use this information. Let's go look at just a few more pieces of information that you're going to need. So we talked about the Kelvin temperature scale. Again, if Celsius is given, you have to add 273 to that to get to Kelvin. Anytime you see STP, you were introduced to that back in chapter 9. So standard temperature and pressure. Standard temperature is 0 degrees Celsius, if I would have written that correctly. 0 degrees Celsius, which would mean 273 Kelvin, and 1 ATM, which is 1 atmosphere. So that's standard temperature and standard pressure. Let's look at some atmosphere correlations, though. So 1 atmosphere is equal to 101.325 kPa. That is kilopascals. Every unit I'm going to give you right now are just more units for pressure. So 101.325 kilopascals equals 1 atmosphere. So I'm giving you some equality statements that you might have to turn into conversion factors at some point. 1 atmosphere is also equal to 101,325 pascals. So we've just taken the prefix kilo off and multiplied that by 1,000. 1 atmosphere, and by the way, kilopascals or pascals is going to be our SI unit for pressure. This is also equal to 760 torr. So 1 atmosphere equals 760 torr, which also equals 760 millimeters of mercury. I know that one's a little bit weird, but they are also equal. And throwing in our English system here, 1 atmosphere is equal to 14.7 psi, which is pounds per square inch. This information you need to make sure you write down in your notes, because you will along the way have to do some conversions, because we need our pressure units to be in the same unit whenever we're doing our calculations. And again, as a rundown, we had Boyles Law, which was PV equals K. Charles's Law, V over T equals K. Gay-Lussac's Law, P over T equals K. And then combined gas law, which is when you're looking at equations that you need to remember, I would just remember the combined gas law equation to use with all of the problems that we are going to do. And again, notice the temperatures have been swapped. So even if you were doing a problem and temperature was constant, you could easily just mark through the temperatures and ignore them and only deal with your P1, V1, P2, V2. And the same goes with, well, what if pressure is held constant? Because you're going to be dealing with Charles's Law. Not a big deal. Just mark out the P's, work with V1, T2, and V2, T1. So again, combined gas law, that is going to be the main gas law for this section, but it can still be applied in any of the 4 scenarios we've talked about. Everything on this slide, you're going to want to make sure that you get in your notes. So let's work out some examples. Gas occupies 473 centimeters cubed at 36 degrees Celsius. Find the volume at 94 degrees Celsius. If I were looking at my given information right over here, I see that I have 473 centimeters cubed. You need to recognize centimeters cubed as volume. So that is the first volume I am given is 473 centimeters cubed. That volume is at 36 degrees Celsius, which is the first temperature I'm given. They go together, so they both get, I'm going to put the ones on those. 36 degrees Celsius, I know I have to add 273 to that to get it to Kelvin. And when you add 273 to 36 degrees Celsius, you get 309 Kelvin. So we're going to have to use the Kelvin point of this. Then I see it says find the volume. So that's the second time volume's mentioned. We're going to be looking for that. I'll label it V2. And this volume is going to correspond to 94 degrees Celsius. So that's the second temperature. They pair up together. 94 degrees Celsius also has to be converted to Kelvin. And when you add 273 to that, you get 367 Kelvin. 367 Kelvin. When I go to work this problem out, I notice that pressure is never given. So even though I'm going to set up my combined gas law equation, there's my combined gas law equation. Again, I notice pressure is held constant because we have no information on it, so I'm just going to mark through the pressures. And my gas law that deals with volume and temperature is Charles's law. Charles's law. So if I had to identify the law, I know I'm dealing with Charles's law, even though I'm going to use my combined gas law equation to plug in information. So we go in and plug in our information, 473 centimeters cubed. T2 is 367 Kelvin. V2 is what we're looking for, and T1 is 309 Kelvin. So when you divide both sides by the 309 Kelvin on each of these, notice your K's cancel. That completely cancels out. So we're left with VT equals something in centimeters cubed. That's good because that is a volume unit. And when you multiply your two top numbers, divide by the 309, you get 562 centimeters cubed as your answer. Make sure you get this entire problem, including the word portion, down. You'll be doing a lot of these problems as we go. The next one, a gas occupies 100 milliliters at 150 kPa. Again, kPa, that's a pressure unit. ml, milliliters, is a volume unit. Find the volume at 200 kilopascals. So for this one, I'm going to just follow through with how the PowerPoint goes through it. So our given information, volume 1 is 100 milliliters. That's at the 150 kPa. So that at first pressure, P1, it's going to be labeled 150 kPa. We're looking for a second volume that's at 200 kilopascals, so the second pressure mentioned is 200 kilopascals. This is the only information I have, so I can see that temperature is held constant. That must mean we're dealing with Boyles Law. Since temperature is constant, we're only dealing with volume and pressure. I still have the combined gas law equation, but now I'm going to mark through the temperatures since I'm not using those, and you'll plug in the rest of your information. To get V2 all by itself, divide the 200 kilopascals that you have here on each side. Notice kilopascals cancels out. This cancels out over here, so we get V2 by itself. So that's 150 times 100 divided by 200, and our answer will be left in milliliters, which is a good volume answer, and you get 75 milliliters. In the next one, so you're writing this down too, a gas occupies 7.84 centimeters cubed. Again, centimeters cubed is a volume unit at 71.8 kPa. That's a pressure unit. and 25 degrees Celsius. So that temperature must be changed over to Kelvin. We're going to find the volume at STP. So again, you have to recall, well, what does STP stand for? That was standard temperature and pressure. Well, standard temperature, so if we're going to find the volume here, that's the second time volume's mentioned. Standard temperature right here was 0 degrees Celsius, which again, you're going to change that to Kelvin. And standard pressure, P2, was 1 atmosphere. But I gave you several pressures that were equal to 1 atmosphere. And one of those pressures I gave you was in kilopascals. So I would leave that pressure in kilopascals, the standard pressure there in kilopascals, so that we don't have to do an actual conversion. So volume 1 is given, pressure 1 is given, and temperature 1 is given, but it has been changed to Kelvin, so that is 298 Kelvin. Then volume 2 is what we're looking for, that STP, standard temperature and pressure. Pressure, that again is from the pressure units I gave you earlier. That is what's equal to 1 atmosphere, but in kilopascals. And you can't see the standard temperature, it's come off of the side over here, so I will write it. Again, that Kelvin should be right there. And if I looked at T2, T2 is standard temperature, which is 0 degrees Celsius or 273 Kelvin, once you add your 273 to 0. Now we're ready to work this out. This is the combined gas law because we're using all three variables, volume, pressure, and temperature. Set this up. We're going to plug in all of our information. There's our P1, V1, and T2, because again, T2 was 273 Kelvin. And all of that equals P2, V2, which is what we're solving for, and T1 is 298 Kelvin. So when you do the math on this one right here, you would divide this side by your 101.325 kPa. That also gets divided on the other side, and your 298 Kelvin, which is divided on the other side, so that all of this cancels, and you will be left with V2. So your final math that you put in your calculator would be 71.8 times 7.84 times 273 divided by 101.325 divided by 298, and your answer is 5.09 centimeters cubed. Again, your kPa's cancel, your K's cancel, you're left with a volume unit of centimeters cubed. Make sure you can put this into your calculator. In the last example, a gas's pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be 560 torr? So our given information, we have 765 torr, which is pressure 1, at 23 degrees Celsius, which is temperature 1. There it is in Kelvin, 296. And then it says at what temperature, so we're going to be looking for T2 that matches up with the second pressure of 560 torr. This is Gay-Lussac's law. Since it only deals with pressure and temperature, volume is going to be held constant. And so we'll mark out V1 and V2, plug in our other information. Once you plug it in, you're going to be solving for T2. So divide both sides by 765 torr. Again, the torrs cancel here, that cancels. You're left with T2 equals. And when you solve for this, your answer will initially be in Kelvin. It'll be in Kelvin. Notice they've also changed it to Celsius. You may run across a problem that says find the temperature in Celsius. You would still have to do all of your work in Kelvin first, then at the very end change Kelvin to Celsius, because the gas laws do have to be in Kelvin first. At the Kelvin temperature scale, I didn't say it earlier, but The lowest temperature is absolute 0 on the Kelvin scale, and that would make sure that we never worked with a negative number for our pressure or volumes.